Hi everyone. In this video I want to talk about black body radiation and how it provides us with evidence supporting the particle theory of light. During the video I'll review what we already know about the way objects radiate electromagnetic light. I'll describe the nature of radiated light from objects as they become hotter. I'll introduce the idea of a black body radiator that is an ideal absorber and radiator of electromagnetic light. I'll look at the predictions made by the wave theory of light and compare them to the actual observations of black body radiators. And finally, I'll describe Maxwell-Planck's quantum-based solution. So what do we already know? All objects emit radiation. This is heat transfer through the emission of electromagnetic light. Everything above 0 Kelvin emits electromagnetic light. The kinetic theory of matter tells us that particles are constantly vibrating. This constant movement of particles provides the generation of electromagnetic radiation. We can't usually see this emitted light because it's usually in the infrared part of the spectrum, or lower in terms of its frequency. That's lower in terms of frequency, but higher in terms of wavelength. As an object gets hotter, the motion of the particles increases and the electromagnetic radiation emitted increases. And when objects get hot enough, they begin to glow. In 1792, Thomas Wedgwood, maker of fine porcelain, noted that all the objects in his ovens began to glow at the same temperature, regardless of their chemical nature. By the mid-1800s, it was known that this radiation was a continuous spectrum. This led to the observation that all the materials that could reach this temperature would glow. It appeared that the type of material was less important than the temperature of the material. As the study of this continued, the idea of a black body was born. The black body is an ideal absorber and radiator of light. It doesn't reflect light. A black body is defined as an object that absorbs all the electromagnetic radiation falling on it. At room temperature, a black body would appear perfectly black, as it would reflect no light, and the light that it emits is dependent upon its temperature only. So the light that it emits at room temperature is in the infrared region only. In the laboratory, a black body would be approximated by studying the behavior of a small hole in the side of an oven. The small hole could absorb light, it could release light, but it could not reflect light. The small hole could not reflect light, so the small hole was the black body. In nature, the closest approximation that we have to a black body would be, ironically, the sun. As experimental technologies improved, it became possible to observe and record exactly which wavelengths of light were being emitted and their intensities for objects at ever-increasing temperatures. The distribution of wavelengths of emitted light followed the patterns of these graphs. There's always a distribution curve, and the distribution curve will always have a peak. Now, in this image that I've taken from the University of Colorado's PhET animations, we see a black body at almost 3000 Kelvin, and it's a very, very small curve with a peak in the infrared region. In this image, we see a black body at 3700 Kelvin. This body might appear to be yellow to us, and its peak in its curve is moving into the visible light range of red. In this body we see a body at 5000 Kelvin. If we were looking at the body, it might appear to be white hot, but it has a peak just inside of the yellow part of the visible spectrum. And here we see a body at 5600 Kelvin, which to us would appear quite white, but its peak in its curve of emitted wavelengths is towards the green section, moving perhaps into the blue. In this image, we see the curves for a black body at 4 different temperatures. The distribution of the curve always has a peak wavelength, and this peak moves towards the lower end of the wavelength spectrum as the peak body gets hotter. So what we see as the body gets hotter is that it will begin to glow. Initially it will be red, then orange, then yellow, and then white. To illustrate this, I can use a rheostat to vary the current through a tungsten filament light globe. As the current increases, the tungsten gets hot and glows. It moves from orange up into yellow, varying in its intensity and varying in its color. As it gets hot, it becomes more intense and moves towards the yellow end of the spectrum. As the current drops, it becomes cooler, it becomes less intense, and moves back into the orange end of the spectrum. In another illustration of this effect, we can look at a mesh sheet when it's placed over a Bunsen flame. As the mesh sheet receives heat from the Bunsen flame, its temperature rises, and we can see that it will start to glow. Initially it'll be a dull red, then it'll move into the orange, the yellow, and then become a bright white as the Bunsen heats it up. As I remove it from the Bunsen, it cools down and it goes back through the colours, from bright white to yellow to orange to a dull red. Here we see it going from bright white to orange to dull red, and heating up again into the white or yellow end of the spectrum with high intensity. Dull red, orange, yellow, white hot. In summary, this is what we observed, and this image shows a black body at 4 different temperatures, so 4 different black body curves for 4 different temperatures. And it summarizes what we've come to see for black body radiation. As objects get hotter, the emitted light increases. The emitted light of a black body is a continuous spectrum. The wavelengths emitted have varying intensities with a diminishing peak wavelength as the object gets hotter. The intensity of the peak wavelength, however, increases as the body gets hotter. As bodies get hotter and the peak wavelength decreases, the bulk of the emitted light shifts toward the visible spectrum. At the end of the 19th century, when these observations were being made, the accepted theory of light was that it was a wave. The wave theory had been the dominant theory since Young's double-slit experiment of 1801. So naturally, it was the wave theory that was used to try and describe black body radiation. The classical response to the black body radiation was the Rayleigh-Jeans law. Unfortunately, while it mimicked observation at low frequency, long wavelength, it dramatically failed to match observation at high frequency and small wavelength. In fact, while peaks were observed in the spectrum for black body radiators, the Rayleigh-Jeans law predicted that there should be no peak at all. This would suggest that an infinite amount of UV and higher frequencies, that is lower wavelengths, should be emitted. This clear failure of the classical model came to be known as the ultraviolet catastrophe. Enter Maxwell Planck. In 1900, Planck made what seemed to be a crazy assumption. He suggested that a black body would receive or emit energy only in discrete little packets. These packets would be proportional to the frequency of the light being absorbed or emitted. With this assumption, he was able to develop what is now known as the Planck radiation law. And in doing so, successfully generated a model for black body radiation that classical wave theory couldn't provide. Planck considered his assumption of discrete packets of energy to be a useful mathematical trick and assumed that eventually someone would find a better way to describe black body radiation that matched existing understandings of energy. History has shown us, however, that this was the beginning of a whole new understanding of energy that would reintroduce the world to the particle theory of light and introduce the world to quantum mechanics.